In this lesson, we will be focusing on the derivatives of inverse functions, and we'll go through this by way of example. So first, the problem we're considering is if we have a function x squared, and the graph of x squared looks something like this, and we're limiting our function to being x greater than or equal to 0. What we'd like to find is the derivative of the inverse of f at x equals 4. So in red, I'll have a picture of the inverse of f. And what we'd like to know is here, when x is 4, what is the slope of the tangent line there? Now, just some things to recall about the relationship between the function and its inverse. The domain and ranges are switched. So when f of x equals x squared, when x has a value of 2, y has the value of 4. So if this is 2, 4 here, then the related point on the inverse is the point 4, 2. And so one thing we want to pay attention to is there a relationship between the two tangent lines? The line that's tangent at 2, 4 and the line that's tangent to the inverse at 4, 2. There are two different methods that you could use to approach this problem to answer the question. The first method is a method that doesn't always work, but when it works, it's pretty nice. So again, what we want to know is what is the derivative of the inverse at x equals 4? Well, one option is to actually first find the inverse function. So if we switch x and y, then we know that x equals y squared. And if we solve this for y, we know that y equals the square root of x. Right, so this is the inverse. And since we'd like to find the derivative of the inverse, well, let's just take the derivative of this. So in this case, y prime would be 1/2 x to the negative 1/2. And we'd like to know specifically what is the value of the derivative when x equals 4. So this would be 1/2 times the square root of 4, which is simply 1/4. Right, so again, notice our first method is simply take our original function, find the inverse, then take the derivative. And that's all fine and good. And that'll work well. But sometimes it's really difficult to find the inverse using that method. So we need a second method to use at times as well. And that method would be something like this. Again, we'll start with our function. And we can always switch the x and the y values, but the problem is going to be sometimes it's difficult to solve for y. But what we can do is take the derivative by implicit differentiation. So 1 equals 2y dy dx. And solving for dy dx, we get 1/2y equals dy dx. And the question at this point is, what is it that we can substitute in for y, right? How can we figure out that value? Well, the relationship we have is in terms of the inverse. We know that x equals y squared, and we know that we're looking at the x value 4, which means that y has to equal 2. And it doesn't equal -2 because we had that domain restriction from the beginning. We're only dealing with x being greater than 0. So we've got +2 as our value for y. That's the value we're going to substitute in, and we end up with the value of the inverse of the derivative as being 1/4. So our first method, when it works, is nice, and our second method of implicit differentiation is what we have to do if we're unsure of how to solve for y, which can happen quite a bit. Some functions simply you won't be able to solve for y again. In this problem, we'd like to find the derivative of the inverse of f of x equals x cubed minus 4x squared plus 7x minus 1, and we'll be looking at x equals 1. Now, the problem with our first method is when we switch x and y, we end up with this function, and it'll be a very difficult task, if not impossible, to solve this for y. So we know that this relates the inverse, but we won't be able to solve for y. But we can take the derivative of this by implicit differentiation. We'll get 1 equals 3y squared dy dx minus 8y dy dx plus 7 dy dx. And solving this for dy dx, and remember in this case dy dx is an expression for the derivative of the inverse, 1 over 3y squared minus 8y plus 7. And so, if we knew the value of y to substitute in, then we can answer our question. And what we want to know is, from that initial relationship of the inverse, when is y cubed minus 4y squared plus 7y minus 1 equal to 1? We're not going to be able to solve this by factoring, and in this case we're not really even going to be able to do much to solve this algebraically. But if we were to graph this and see when this equals 1, we'll find that graphically this will equal 1 when y is about 0.349. Alright, so now we're using our calculator to help us out. And this means that when we substitute in 0.349 into our expression, so it'll be 3 times 0.349 squared minus 8 times 0.349 plus 7, and we solve for dy dx, we're going to get about 0.219. It's roughly the slope of the inverse. Let's consider another example. Here our function is, I'll erase it. Our function is e to the x plus ln x, and we'd like to find the derivative of the inverse at x equals 3. Again, we won't be able to find the inverse directly, but we can begin that process, and we'll need to solve for dy dx by implicit differentiation. So 1 equals e to the y dy dx plus 1 over y dy dx, which means that 1 over e to the y plus 1 over y equals dy dx. Or if we simplify the denominator a bit, this will end up being y over y e to the y plus 1. We just multiplied numerator and denominator by y to get this form. And if we knew what value of y to substitute in, we'd be able to solve for this. So, going back to our original inverse relationship, we know that e to the y plus ln y would like to know when that equals 3. We won't be able to solve that algebraically, but graphically we can figure out when this is the case, and we'll find that this will occur when y is about 1.074. So, substituting in 1.074 over 1.074 e to the 1.074 plus 1 gives us an approximate value of 0.259 for dy dx. Let's do one more example. Here we'd like just to find the derivative of the inverse of y equals e to the x squared. So the inverse function would be x equals e to the y squared. If we could solve this for y, that'd be great. And we can, because this is currently in exponential form, but we can rewrite it in log form. The base is e, so the natural log of x should equal the exponent, in this case y squared, and taking the square root of both sides, we know that y should equal the square root of x. The derivative of this then, y prime, would be 1/2 times the natural log of x to the negative 1/2 times the derivative of the inside, in this case 1 over x. And if we clean this up just a bit, we get 1 over 2x times the natural log of x to the 1/2 power. So if we can use method 1, like we could in this case, now we could just substitute a given x value and we'd know the value of the derivative of the inverse. Or, like the previous examples, sometimes we have to use implicit differentiation in order to find the derivative.